So we want to look at this one first. So this is b plus 1 over b minus 3 minus 2. So we want to think about all of these as rational expressions, which means they all need a numerator and a denominator. So if we just have b, then that means the denominator is 1. That's like b over 1. Then that's like 2 over 1. So that means the only denominator which is not equal to 1 is b minus 3. That means we need to build each of these terms up until we have that same denominator. So I'll multiply this by b minus 3 over b minus 3, and then we'll do the same thing here. Multiply this by b minus 3 over b minus 3. All right, so let's see what that gives us. So that's going to give us b squared minus 3b. So that's what we get from distributing this b onto each of those terms over b minus 3. And then we have that as plus 1 over b minus 3. And then minus, well, now we distribute that 2 through. So that'll be 2b minus 6 over b minus 3. The next thing that I'd like to do is take this minus sign, which is outside of this entire fraction, and maybe distribute it through to the terms in the numerator so the calculation is a little bit more transparent. So I'll take this, distribute it through. It's going to turn that into a plus if I make that a minus and that a plus. So I changed all of those signs. Now, since I have a common denominator here, I can just add everything. So I have b squared. Then I have minus 3b minus another 2b, so that's going to be minus 5b. And then next I have 1 plus 6, so that's going to be plus 7. Okay, good. And now notice that's all over b minus 3. Now we want to see if we can factor this. So can we factor this b squared minus 7b plus 7? And I think you can see that you cannot factor it because the only way to write 7 is 7 times 1 because it's prime. But 7 times 1, well, 7 and 1 cannot add up to give you, or add or subtract to give you 5. So there's no way to factor this numerator. So that's as simple as this thing can get. All right, now let's go ahead and look at this next one. So for this next one, we've got 2x over x minus 4 minus 1 over 2x plus 1. We want to do the same kind of thing. In this case, we've got two terms that have a denominator which is not equal to 1, but we'll need to build them to have a common denominator. So the common denominator will be the product of x minus 4 and 2x minus 1. So let's go ahead and do that. That means we're going to multiply this first term by 2x plus 1. We need to build the denominator up to that common denominator. And then we're going to multiply this second term by x minus 4. Again, building that up to have the common denominator. So let's see what that gives us. We got to take this 2x and distribute it onto both of these. That'll leave us with 4x squared plus 2x over 2x plus 1 times x minus 4. That's what we have there. And then, I mean, technically we're taking this 1 and distributing it onto that x minus 4, but that doesn't change anything. So we get minus x minus 4 over 2x plus 1 times x minus 4. And now we have common denominators. So we can simplify that, a lot more easily. So I'm going to do the same kind of thing I did here. This minus sign is attached to this entire fraction. So I want to distribute it through to the parts of the fraction so that I can combine these a little bit better. So I'll change this to a plus by changing that to a minus and that to a plus. In other words, changing the sign of everything in the numerator there. So let's see what that gives us. We're going to have 4x squared, and then we'll have minus x, and then we'll have 2 plus 4 is 6. So we'll have that 4x squared minus x plus 6. That's what we're left with in the numerator. And then in the denominator, we have 2x plus 1, x minus 4. Now, perhaps we can factor out that numerator in a way that will cancel with something in the denominator. So we should probably check that. And another thing is that built into this problem is maybe a hint of how it would factor. It's not so much a hint as it is, well, this way of factoring would cancel with the denominator, but no other way would. And that would be involving a 2x plus 1. So let's see if we can factor it with a 2x plus 1. So that means we would need 2x plus 1. And then next we would need 2x. Well, let's see what else we would need. So we need another 2x because 2x times 2x is 4x squared. But then if we have plus 1 and then we have a 6 here, then we need a plus 6. But now notice that does not give you 4x squared minus x minus 6. So that is not the factorization. So I'm not saying this won't factor, but it won't factor in a way to give us a 2x plus 1, and that's really the only helpful way of factoring to simplify this. Notice it's also not going to factor with an x minus 4 because 4 is not a divisor of 6, which is what it would take to factor with that. So, all of that being said, this is the simplest version of this expression. Okay, cool. So I want to do one more round of this, and I know like maybe we took our foot off the gas a little bit, but I don't know. It's my experience that this stuff is kind of tricky, so it's nice to take our time and practice this as much as possible. And so that we're taking the advantage of that. We have the time to do that. So again, let's do another round of this. So the problems are on Moodle, but I'm going to write them on the board also. Okay, so the last round will be 1 over x plus h minus 1 over x over h. So this seems maybe like it's needlessly complicated, but this object is actually super important when it comes to something you do in Calculus 1. So doing these kind of calculations will be helpful, moving forwards for that goal. Then let's say the other one is t to the minus 1 plus t to the minus 2 over t to the minus 3. And I should say, well, how do we want to simplify that? Let's simplify that so that there are no negative exponents. Okay, so I'll give you guys 3, 4, 5 minutes to simplify these, and then we will look at them together again, and then move on to looking more in depth on rational equations. So let's go ahead and look at these last two warm-up problems, and then we will go ahead and look at equations involving rational expressions. So this one's like a little bit more complicated. We've got this complex thing in the numerator, which is itself a sum of two fractions, and then we've got a denominator. So there's actually a trick that you can do in this case, which is a nice simplification, and that is you can clear the fractions in the numerator if you multiply something in the denominator as well. So maybe let's go ahead and do that. I think we simplified something like this a different way last class, so I'll let you guys look back at that if you want to see the other method, but I think this method is nice in that it skips some steps. So I'm going to go ahead and maybe put some brackets around this so we recognize that it's grouped together. Now what I want to do is multiply this numerator by something so that the fractions are cleared. So I can multiply by x times x plus h. But I can't freely multiply by x times x plus h because that's going to change the value of the expression. But if I also divide it by x times x plus h, then I haven't changed anything because I've multiplied by something over itself, which is 1. Now, this kind of thing is only applicable when you've got this kind of complex fraction situation with fractions in the numerator and the denominator. That allows you to multiply by something but undo that multiplication in another spot. As we'll see when we solve these rational equations, we'll also use this trick, you know, from time to time. Okay, so let's see how this goes. So if we multiply this x times x plus h through to the numerator, notice in the first term of the numerator, the x plus h term is going to cancel. That leaves us with just x. You know, let's maybe notate that. So this thing right here becomes our x. And then this thing right here, when the x times x plus h multiplies onto it, the x's will cancel, and we are left with x plus h. So that is this term. So again, to reiterate, that's what we get from taking this x times x plus h and distributing it onto the blue and the green. So I've underlined them like that. Okay. So now that's going to be all over h times x plus h. So the h was already there, and then we introduced the x times the x plus h to undo what we did in the numerator. Okay, now next what we want to do is maybe distribute this minus sign across these terms in the numerator, so I can turn this into a plus if I turn this into a minus and this into a minus. That gives me x minus x, so those are going to cancel, and then I'm left with negative h in the numerator. So we've got x minus h after everything is expanded. And then this is going to be all over h times x plus h, like that. But now we can see that this h will cancel with this h, leaving us with just a 1 in the numerator. So that means our final expression is negative 1 over x times x plus h. And that's as simple as you can make it. Okay, good. So now let's go ahead and look at this one. So we've got a bunch of negative exponents there. So maybe we want to change those negative exponents to exponents in the denominator. So let's maybe recall real quick that if we have a to the minus n, that's the same thing as 1 over a to the n. So a negative exponent is the same thing as a positive exponent after that thing has been sent to the denominator. So that means I can rewrite this as 1 over t plus 1 over t squared over 1 over t cubed. Now what I want to do is take the same strategy that I did for this first problem. Notice I've got this. If we have t to the minus 1, we write the minus 1, but if we have t to the 1, we don't write the 1. So that kind of gets gobbled up in our just notation or whatever. Okay, so we've got the same kind of setup that we did in this example. We've got this complex combination of rational expressions. We've got a sum of two fractions in the numerator, and then we've got also a fraction in the denominator. So again, there are a couple of ways that we can simplify this. We could just combine the terms in the numerator by finding a common denominator. But my favorite way to do this would be to instead multiply the numerator and the denominator, and I mean kind of the larger numerator and denominator, by something so that those fractions are gone. And I can do that by multiplying the denominator and the numerator by t cubed. So notice multiplying the denominator by t cubed is just going to give me 1. So that's cool. And then multiplying the numerator by t cubed will also get rid of those fractions. So let's see what we get. So I'm going to take this t cubed, and that's going to distribute onto each of these terms, keeping in mind that we have grouping here. So the first one, we have t cubed over t, so that's going to give us t squared. The second one, we have t cubed over t squared, so that's going to give us t to the 1. And then in the denominator, we have t cubed over t cubed, so that's just 1. But now, generally if we've got a fraction with 1 in the denominator, we don't write that, so we can just rewrite this as t squared plus t. And that would be like maybe as simple as we could make this expression. Okay, good. So now what I want to do is take these techniques involving simplification of rational expressions and apply them to solving equations with rational expressions. So let's do that. We're going to do like a couple of examples of like each family, and then after each couple of examples, we're going to try one or something. Okay, so let's maybe look at this. Well, actually, let's maybe recall a fact that we had from last time. So if we have an equation, P of x over Q of x equals 0, then the solutions are when P of x equals 0 and Q of x is not equal to 0. Now I'm writing this just in one case where we've got the rational expression equal to 0, but this holds for any types of equations involving rational expressions. If you get a solution that when plugged into the original expression gives you a 0 in the denominator, then that was actually not a solution. So we saw this last time where we had to check all of our solutions to make sure that none of them gave us a 0 in the denominator. And if they did, those were not allowed to be solutions. So let's just keep that in mind. We don't want zeros in the denominator. If we get a solution where there's a 0 in the denominator, we have to throw that one away. Okay, so moving on with examples, let's first look at x over 5x plus 4 equals 3. So notice this is not of the form P of x over Q of x equals 0, but that's okay. We could move the 3 over and then it would be of that form. But the fact is that there's actually a simpler way to do it. And that is by cross multiplying. So we did a lot of cross multiplying to solve equations when we just had numbers in the denominator, but we can also do that when there are like polynomials in the denominator as well. So I want to think about this as 3 over 1, and then I can just cross multiply. So I'll multiply this 5x plus 4 up and this 1 up, and that's going to give us x equals 3 times 5x plus 4. But now that's a linear function from like the first week or so of class, so that's not too hard to solve. So we've got x equals 15x plus 4. We can go ahead and move this 15x over. That's going to give us minus 14x equals 4. We can divide. We'll get x equals 4 over 14. And that's going to be negative because we got a minus sign. And then we can reduce that. Notice we can divide 2 out of the numerator and the denominator. That gives us negative 2 over 7. So that's our solution. And now what we want to do is check this. And by check it, I mean you want to throw it into the original equation and notice that there are no zeros in denominators. And so that means that this checks out okay. We can keep this solution. So let's say we plug this solution back into our original equation, and that gave us a 0 right here. Then you'd have to get rid of that, and there would not be a solution in this case. So I would say the appropriate strategy for most of these is to do a simplification so that you get rid of the fractions, but then after getting rid of the fractions, you solve it as normal, keeping in mind that at the end, you have to check to make sure you didn't get a 0 in the denominator in the very first equation. So that's sometimes called an extraneous solution. So you want to check that you did not uncover an extraneous solution. All right, let's look at another one. So let's look at this. 1 over w plus 3 plus 1 over w minus 3 equals w squared minus 3 over w squared minus 9. So we still want to do like the same strategy as we did over here, which is essentially multiply by something that clears the denominators, which is what we did here. We just had cross multiplication. We can't cross multiply here because we've got a sum on the left hand side. That's like a little bit more complicated. We can't just straight up cross multiply unless we've got one object on the left hand side and one object on the right hand side. But what we can do is look at all of the denominators that are present and multiply by something that will cancel all of those denominators. And that something is not super clear unless we factor all of the denominators. So notice this w plus 3 won't factor anymore. That w minus 3, that won't factor anymore. But this w squared minus 9 will factor. And that factors as a difference of squares. So let's maybe notice that this w minus 9 will factor to w minus 3 times w plus 3. That's one of our like standard factorization formulas, the difference of squares factorization. But notice w minus 3 and w plus 3 are the denominators that are available over here on the left-hand side of the equation. Maybe I'm going to write this again just so we don't lose anything. So we've got that equals w squared minus 3 over w minus 3 times w plus 3. So I've just factored that denominator on the right-hand side. And that gives me a huge hint of what I can multiply this entire equation by to cancel the denominators. So notice if I multiply the entire equation by w minus 3 times w plus 3, I'm good to go. So that's just going to straight cancel this denominator, and it's going to cancel these denominators, but we're going to get some extra stuff. So let's see what we have. We'll take this and we'll distribute it on to each of these terms. So notice distributing it on to this 1 over w plus 3, the w plus 3 will cancel, and we'll be left with w minus 3. Then next, distributing it on to this w minus 3, we'll see that the w minus 3 will cancel and we'll be left with w plus 3. And then finally, distributing it onto this term, we'll see that the entire denominator will cancel with the entire numerator because they're equal there, and we'll be just left with this w squared minus 3. So that's what we're left with. So now we can start combining like terms. Notice that we've got a polynomial equation, so we want to move everything to one side and then just have 0 on the other side. Factor quadratic formula or something. So let's see what that'll give us. We'll have w squared. Then notice this adds up to 2w. We can move that over. So it'll be minus 2w. Then next we see that minus 3 plus 3 is equal to 0. So we've got minus 3 equals 0. So just to kind of reiterate what happened here, this minus 3 and this plus 3 canceled. And then this w and w added to 2w and we moved it over. Now we want to see, can we factor this or solve it some other way by using quadratic formula or something. But I think factoring will work here. Notice we want two numbers that multiply to -3 and they add to 2, well, -2. So I think -3 and a +1 will work. Let's just make sure that works. We get w squared, that's good. -3w plus w, that's -2w, that's good. -3 times 1 is -3, that's good. So that tells us that we have two equations, w equals 3 or w equals -1. Again, by the product of two things being equal to 0 means one of them has to be 0 rule. Now, the important thing that makes this different than if we had just started right here or right here, for instance, is that one of these solutions is extraneous. And that is because if we take this w equals 3, plug it back into the original equation, notice that gives us a 0 in the denominator right there. We have 1 over 0, but 1 over 0 doesn't make any sense. You can't divide anything by 0, which means you have to discard this solution. because when we plug it into the original equation, we get a 0 in the denominator, which tells us that this w equals -1 is actually the only solution. We had to throw out the other one. It is a so-called extraneous solution. Okay, so let's maybe try one real quick, and then we'll do another type of problem like in this vein. I'll give you guys 2, 3, 4 minutes to try this, and then we'll go over it. T squared minus 2t plus 1 over t cubed plus t squared minus 2t equals 1. Okay, so let's go ahead and look at this one. So this is a kind of a combination of the last two, in that all we have to do is cross multiplication. We don't really have to worry about like looking at a bunch of terms and figuring out what the greatest thing is to kill the denominator, because we've got a simple setup on each side of the equation. So getting rid of the denominator is as simple as multiplying by this t cubed plus t squared minus 2t, which is like cross multiplying here. But it's a higher order equation. In other words, it's not a linear equation. It's like a cubic equation. Okay, so let's see what we get if we cross multiply or equivalently multiply this whole equation by t cubed plus t squared minus 2t. So let's see what that gives us. That's going to give us t squared minus 2t plus 1 equals t cubed plus t squared minus 2t. Something like that. Now, since this is a polynomial equation, we probably want to move everything to one side of the equation and set it equal to 0. That's kind of a standard method here. So let's go ahead and do that. Let's take this and subtract it all over to the other side of the equation and see what we get. So that's going to leave us with t cubed. Then next, we'll see that we have t squared and t squared, but those are going to be subtracted. So that's nice. And so that's going to give us 0. So in other words, we've got t squared minus t squared, that moves over. The 2t terms do the same thing. So we'll have a negative 2t minus a negative 2t. That's going to cancel as well. And then we're just going to have this 1, which gets moved over. So that will be minus 1 equals 0. Okay. Now what we want to do is find a way to simplify that. And if you recall from what we did with factoring, we have a factorization of this with a difference of cubes. So we saw that in one of the warm-ups, but it's popping back up here. So we've got t minus 1 times t squared plus t plus 1 equals 0. So that gives us two possible solutions. That gives us one solution, which is t minus 1 equals 0, which means t equals 1. And that gives us another solution when t squared plus t plus 1 equals 0. Now, we have to try to factor this or use the quadratic formula. If you try to factor this, you'll see that it doesn't seem likely to factor, so we'll need to use the quadratic formula. That means t equals negative b, that'll be negative 1, plus minus the square root of b squared, that's 1, minus 4ac, that's going to be minus 4 all over 2 times a, but that's 2 times 1. So that's our quadratic formula expansion for the solution of this. But the important thing to notice here is that this thing is less than 0. 1 minus 4, well, that's negative 3. So we've got the square root of negative 3. But for our setup, we're only working with real numbers, not complex or imaginary numbers. So this actually gives us no solution. Because, well, the discriminant is negative. Remember, we called the discriminant this stuff under the square root, and if the discriminant is negative, then you have no solution because you're taking the square root of a negative number. So that means this t equals 1 is our only solution. So now let's maybe check to make sure that this is actually a solution. So if we plug t equals 1 up here, we'll have 1 cubed plus 1 squared minus 2 times 1. Oh, but that's equal to 0. So in other words, our solution makes the denominator of the original equation equal to 0. But that's something that we do not want to happen, which means this is actually not a solution. It's an extraneous solution. So it is, maybe I'll put it in quotes, extraneous. It's extraneous solution. So the only possible solution was an extraneous solution. So that means there is in fact no solution. So over here it looked like t equals 1 was a solution, but t equals 1 made the denominator of the original setup equal to 0, but that's not allowed when we're finding a solution. So in fact, this was not a solution. But if our only solution is not a solution, then there's no solution. I just said solution like 65 times. Okay, so a little bit tricky in that there are a lot of little calculations to do, but if you break it down into all of these parts and remember all of the little details, it's not too terrible. Okay, so let's go ahead and look at a couple more of these. I want to look at one involving absolute values, and then one involving solving a rational equation for one variable when there are maybe more than one variable. Okay, so first I want to look at one where there are absolute values, just to kind of show how you would deal with an equation with rational expressions and absolute values. So let's maybe look at this one. Absolute value of 2z over z squared minus 4 equals absolute value of 2 over z minus 2. All right. So if you recall from when we were originally doing equations involving absolute values, we had the following rule. If the absolute value of capital A was equal to the absolute value of capital B, then A was equal to plus or minus B. And so this plus or minus allows us to split this up into two equations, one built off of the plus in the plus or minus and one built off of the minus in the plus or minus. But then after we've split it into two equations, we can solve each of those using the methods that we've just talked about. So essentially, an absolute value equation is just a hidden version of two equations that we've already tackled. Okay, so let's go ahead and do that. So we've got 2z over z squared minus 4 equals 2 over z minus 2. So that would be the plus. The plus is just removing the absolute values without doing anything. And then 2z over z squared minus 4 equals negative 2 over z minus 2. So that would be the minus version. Now we want to solve each of these individually. So maybe the first thing that I want to notice is that, well, maybe we can look at the denominators here and see if we can multiply by something to clear the denominators. You could also cross multiply, but that's maybe a little overkill here. So let's notice that we can take this z minus 4 and we can factor it as z minus 2 times z plus 2. And we can do that over here too. So z minus 2 times z plus 2. And writing it like that is actually helpful because we can, instead of cross multiplying, just multiply by this denominator and get some nice simplification. So let's take this entire thing here and multiply by z minus 2 times z plus 2. Same thing over here. We'll take this, multiply by z minus 2 times z plus 2. So I put those over each other, but it's multiplication. Really, I just ran out of horizontal space. Okay, so distributing this onto the left-hand side of this equation will just cancel the denominator. So the z minus 2 cancels the z minus 2, and the z plus 2 cancels the z plus 2. That just leaves us with 2z in the numerator. Now let's see what we get over here. The z minus 2 will cancel this z minus 2, and then we'll have 2 times z plus 2, so that'll be 2z plus 4. After distributing this through, right? So 2 times z, 2 times 4. That leaves us with this, but now notice we can subtract 2z over. That gives us 0 equals 4. That doesn't make any sense. 0 is not equal to 4, so that tells us that there is no solution down this line of reasoning. Now we want to repeat this over here. So multiplying by z minus 2 times z plus 2 to the left-hand side will give us 2z, just like it did over here. Multiplying to the right-hand side will give us minus 2z minus 4. Again, the minus 2 is going to multiply through to the z plus 2 because the z minus 2 cancels. Now we can move this over and we get 4z equals negative 4, which makes z equal negative 1. Now we want to go up here and make sure that plugging in z equals minus 1 to our original equation does not make the denominator equal to 0, but it doesn't. Notice plugging it in here makes the denominator equal to negative 3. Negative 3 is not 0, so we're A-okay. Plugging it in here makes the denominator also equal to negative 3, kind of for another reason, which is also not equal to 0, so we're okay. In other words, the denominator does not become 0 when it plugs into the original equation. So this is an okay solution. We can keep it. We don't have to throw it out. Okay, so let's do one more. This is going to be solving one of these rational equations for one of the variables when there are potentially more than one. So let's say maybe this one. I think this one is nice and tricky. So maybe 1 over x minus y plus 1 over x plus y equals 5. And let's say we want to solve for x, where we've got x and y are both variables. Okay, so we want to take the strategy that we did for one of the earlier problems, and that is multiply by something to kill the denominator. Notice, to kill the denominator here, the best thing that we can do is multiply by x minus y times x plus y, the product of these two denominators. That's as simple as we can get in this case. So let's see what that gives us. Taking this x minus y times x plus y, multiplying it onto this first term will give us x plus y. Multiplying it onto this next term will give us x minus y. So we'll get that. So again, that's multiplying on the first term, x plus y, because the x minus y cancels. Then likewise, the x plus y cancels in the second term, and we're left with x minus y. And then over here, we're going to get 5 times x minus y times x plus y. Now let's maybe go ahead and simplify both sides of this equation. So notice the y's cancel on the left-hand side. That leaves us with 2x. And then on the right-hand side, that's going to multiply out to 5x squared minus y squared. Something like that. Now we have a polynomial. Here we want to think about this in the following way. X equals a variable. And then y, well, it's an unknown also, but it's an unknown which is playing the role of a constant in this case, and that's because we want to solve for x. So we can rewrite this as something like a quadratic polynomial where x is the variable. So let's go ahead and do that. We've got 5x squared minus 2x minus y squared equals 0. Now we can use the quadratic formula. And so it's a little bit tricky because our constants involve y in this case. So I'm just going to write this out carefully. So we use the quadratic formula. Remember, the quadratic formula had these constants a, b, and c. Recall it was like ax squared plus bx plus c equals 0. Well, in our setup, we have a equals 5. We have b equals -2. So those aren't too hard to see. But then we have c equals -y squared. So c is this weird thing that depends on y. But that's okay, we can still use the quadratic formula involving something weird like that. So let's see what that gives us. So we'll have x equals -b, so that's going to be 2, plus minus the square root of b squared, so that's 4, minus 4 times a times c, so that's going to be plus 20y squared. So 4 times a times c, 4 times 5 is 20, times c is, well, that's a -y squared, but there's a minus sign built into the quadratic formula. Here, let's maybe go ahead and write that. Here we have x equals -b plus minus square root of b squared minus 4ac all over 2a. That's what we're using here. And so we need the all over 2a, so that's going to be all over 10. So that's actually as good as you can do for solving for x. So this is what we would have solving for x in terms of y in this setup. So notice we've got this 4 plus 20y squared under the square root. We can't simplify that, and well, maybe we can factor a 4 out of that and take the square root of 2. I'll leave it to you guys to think about that, but there's nothing really substantial that we can do to simplify this. Okay, so I didn't post a homework from last Thursday because I wanted to take the opportunity to take today again to review a bunch of this stuff, but I will post a homework for what we did today, which I guess by our schedule will be due on Saturday, involving like simplifying these rational expressions and solving these rational equations. Just to reiterate what I said at the very beginning of class, in case you missed it, if you are missing any homework, I'm happy to extend the deadlines given the circumstances of the universe right now. Just like maybe send me an email by this afternoon and I'll do all of those this afternoon. I'll edit down the video from today either later today or tomorrow and post it if you guys want that. We'll have we'll have an exam next Thursday. I think that's everything. I think I reiterated like everything important coming up. Is there anything else that you guys want me to say before we're done with class? That's a really weird thing to say.